Crankshaft production doesn't just demand accuracy, it depends on it. This video takes us inside the VDF Boringer line, where modular machines like the VDF 221 and VDF 226 handle each operation with unwavering consistency. The process begins with machine assembly and setup. Components are positioned on a conveyor and automatically fed into the system via a gantry loader. Dual turning and broaching operations are seamlessly integrated, allowing the machine to rough out and finish multiple surfaces in a single setup. Watching these tools in action, cutting, shaping, and broaching, reveals the harmony between power and precision. These machines can perform multiple machining operations in a single clamping, significantly improving both speed and accuracy. Parts are automatically transported between modules using a gantry loader, minimizing manual handling and keeping the workflow fast and steady. It's impressive to see how efficiently the gantry system coordinates with the machines, delivering each component to the next operation without missing a beat. The external milling station focuses on machining pin journals with high rigidity. Specialized tools mill away excess material, ensuring pin geometry meets strict tolerances. For internal features, high-speed cutters shape the main bearing surfaces and pin bores with remarkable accuracy. The production line incorporates roller burnishing, a process where a hardened roller is pressed against the metal surface while turning, creating an ultra-smooth finish that improves fatigue life and dimensional consistency. This step is essential for critical crankshaft surfaces, and the results are always visually satisfying. Throughout the entire sequence, modular machine design makes it possible to tailor the setup for various crankshaft types and production volumes. Quick change tooling and cross-sectional views allow technicians to monitor, adjust, and maintain the system with minimal downtime. What really stands out is the combination of automation, flexible machine architecture, and uncompromising quality control. Every detail, from the initial turning to the final inspection, reflects a commitment to reliability and high performance. It's a fascinating look at how advanced manufacturing turns tough materials into vital engine components that keep the world moving. Each year, over 1.2 million self-aligning roller bearings roll off 33 production channels in Gothenburg. Steel rings up to 2,500 millimeters are heat-treated using a two-step bainite process, reducing ovality and cycle times. Floating rollers self-adjust to stress, lowering friction. Visual buffers spot deviations early. This is engineering discipline at its finest. These boats are built tough, really tough. At the Wisconsin and Florida facilities, each hull begins as a thick HDPE sheet, engineered for strength, UV stability, and full recyclability. CNC routers cut every panel with precision, shaping both standard and custom designs to exact tolerances. Welders then use high-temperature extrusion welding to join these panels, producing seams so robust that even sledgehammer blows can't crack them. Every weld is checked, and any imperfection is ground down until the surface is seamless. The hull's durability comes not just from the material, but also from this obsessive attention to detail. It's amazing to see how the process combines automation and skilled hands at every stage. HDPE's resistance to corrosion and marine growth means there's no need for bottom paint, and owners won't worry about repairs due to rot or rust. Each assembled hull is inspected, then tested for watertight integrity and structural strength. Boats are subjected to impacts and stress tests. Seeing the hull flex and recover is genuinely impressive. You can tell the focus on reliability is woven into every layer of the build. This process isn't just about building boats, it's about creating platforms that thrive in the harshest conditions, whether it's military rescue or commercial use. What really stands out is how lightweight these hulls are, despite their toughness. The team's pride in every step is obvious. Their years of experience show in the flawless finish and innovative fabrication. Transforming simple HDPE sheets into vessels that shrug off abuse is no easy feat. The combination of technology, technique, and hands-on craftsmanship is simply captivating. Fixed steel plates are explosion-clad, bonding dissimilar metals in milliseconds. Sparks cascade as arcs melt steel edges together, watching molten metal fill the groove. This is raw fabrication energy you don't see every day. The transformation of steel into powerful springs starts with massive coils unwound and straightened ready for shaping. In the first stage, rods are heated in a blazing furnace, their color shifting to a vivid orange as they reach forming temperature. The intensity is captivating, raw energy in motion. Red-hot blades are quickly moved to forming machines where each is ground, compressed, or cut to precise dimensions. Sparks fly as tools shear and trim the ends, the whole process blending with force and control. Next comes quenching. Springs are plunged into oil and water baths, their surfaces evaporate flash and fire. This sudden cooling locks in material hardness and strength. Watching the steel bend is truly dramatic. Each spring emerges shaped, ready for heavy duties. The springs then undergo grinding and coiling, typically large and small parts to exact tolerances. Calibration and load testing follow, using automated presses and digital sensors to guarantee performance under real-world stresses. Some springs are shot-peened, their surfaces bombarded with tiny steel balls to increase fatigue resistance. Surface finishing, zinc plating, painting, or phosphate coating provides corrosion protection and a flawless look. Every step reveals the blend of heat, force, and precision. It's a continuous rhythm, from fire to form, from tension to tested power. There's a unique satisfaction in seeing industrial springs brought to life, built not just to flex, but to endure. This isn't just a robot, it's a giant. Weighing 9,461 kilograms, the MH900 is built for moving payloads up to 900 kilograms with precision. Each unit begins as a massive frame, assembled using 1,169 bolts, 253 of them M20 or larger, torqued at heights over 1.7 meters. Workers align each arm module and motor assembly, then test the torque load paths before moving on to axis calibration. The upper arm alone stretches 4.186 meters, and every millimeter matters. Watching these engineers thread torque wrenches into place is like watching heavy-duty surgery, but with 100% steel. Vertical reach peaks at 6.209 meters, with full motion across 6 axes. The counterweight alone is over 1.2 tons, giving the robot the stability it needs for casting extraction, die changes, or shifting entire car frames. Once assembled, it's tested under simulated loads. The fixture mass moment of inertia, 2,200 kilogram-meters squared. That's not just a number, it's a promise of stability under serious force. Seeing this monster stretch and rotate with absolute control feels surreal. When engineering meets raw mass like this, it becomes something else. Pure, functional muscle. Massive precision at a century-old dam. At Sir Adam Beck 1, teams removed the original scroll cases after realizing repairs were no longer viable. New scroll cases were engineered, fabricated, and installed under tight tolerances. Each section had to align perfectly for water flow stability. Heavy lifts, custom welding, and confined access made the work especially demanding. Completing this during a pandemic? That's serious execution. Watching century-old hydro parts replaced with modern engineering, it's like watching time renew itself with steel. The hum of stamping presses fills the air as raw metal takes shape under immense force. At Betcher Manufacturing, every stamped component starts as a coil or sheet of steel, aluminum, or copper, chosen for precise requirements. The plant runs over 46 stamping presses, each with capacities from 60 to 900 tons, shaping the metal into simple clips, intricate brackets, or deep-drawn housings. It's remarkable to see the variety formed through perfectly controlled force. Freshly stamped parts go through washing and phosphate lines, removing oil and prepping each surface for the steps ahead. Value-added processes follow: machining, tapping, welding, assembly, press brake forming, grinding, vibratory finishing, or deburring. Watching machines and skilled technicians work together in sync adds a sense of engineering rhythm to the whole operation. Surface finishing is next. Plating and coating are handled by strategic partners, adding corrosion resistance and a clean look to select parts. Quality is maintained through statistical process control, tracking measurements and process parameters to ensure every lot meets exacting standards. The metrology lab is where precision is put to the test. Coordinate measuring machines and digital measuring devices examine tolerances, geometric features, and critical dimensions. ISO 9001 certification is an everyday benchmark for quality, not just a wall decoration. Environmental responsibility is obvious here. Wastewater is treated 100%, reusable containers are used wherever possible, and a focus on industrial safety keeps every shift running smoothly. Technicians in key technical roles drive efficiency, reliability, and continuous improvement. Once complete, components are packed and shipped across the United States, Mexico, and beyond, supporting customers with a 98.5% on-time delivery rate. Seeing raw material move through stamping, cleaning, value-added finishing, inspection, and shipping is a testament to manufacturing excellence and the teamwork that makes it possible. At Betcher, precision is not just an outcome, it's the foundation of everything. This is aluminum rotor recycling in action, fast, loud, and relentlessly efficient. It begins when discarded rotors are dumped into the feed hopper of a hammer mill shredder. Inside, high-speed rotating hammers pulverize the rotor bodies into manageable pieces. The raw power of this machine is something you don't just see, you feel it. The shredded output lands on a vibrating conveyor, spreading fragments evenly for processing. A built-in magnetic sorter then removes ferrous metals, such as steel shafts and screws, ensuring the remaining aluminum flows downstream free of contaminants. Here's where things get clever. The shredder is precisely tuned to break apart components without overheating the aluminum, preserving its physical properties. Magnetic separators are angled to optimize extraction without halting the conveyor's momentum. Every part of this system is engineered for throughput and material purity. Clean aluminum fragments exit the line ready for melting, extrusion, or casting. No manual sorting required. This isn't just waste management, it's resource recovery at industrial speed. The machines hum with purpose. Operators monitor vibration levels, shredder loads, and magnet efficiency through sensors and manual checks. Adjustments are made in real time to maintain output consistency. Even slight shifts in material flow can trigger tweaks in conveyor speed or shredder torque. Safety is no afterthought. Emergency shutoffs, shields, and thermal controls are built in. The process is contained, controlled, and repeatable. You're watching a material rebirth. Each crushed rotor represents more than scrap. It's opportunity reclaimed. The transformation is gritty, but the outcome is valuable. It's easy to be impressed by the raw destruction, but the real magic is in how that chaos gets harnessed, sorted, and turned into usable material again. That's recycling done right, with speed, precision, and a clear purpose. A carbon fiber wheel isn't just a product. It's the result of engineering, hands-on skill, and absolute attention to detail. Let's step inside the factory and watch the transformation from soft fabric to high-performance rim. The process kicks off with carbon fabric. Sheets are carefully unrolled, inspected for imperfections, and precisely cut according to computer-modeled templates. The orientation and alignment of every strip matter. A difference of just a few degrees can impact the finished wheel's stiffness and ride quality. Rim straps and braking ribbons are added next. These pre-built layers are integrated by hand, positioned in just the right place to reinforce areas subject to the highest loads. It's a job requiring patience and a sharp eye. When the layup is complete, it's more than a stack of fabric. It's the DNA of the wheel. Small sensors embedded in the mold monitor pressure and temperature throughout the curing cycle. Semi-finished layups are moved to a two-part mold. Here, membrane pressure is applied, and the whole assembly is heated between 180 degrees Celsius and 190 degrees Celsius for a full hour, followed by a 15-minute cool-down. This high-temperature cure bonds resin and carbon, locking the fibers into a single, seamless structure. Once the mold opens, the rim takes shape, rigid, feather-light, but unfinished. Next comes precision drilling of spoke holes, using jigs that guarantee exact position, depth, and angle. A single misaligned hole can compromise wheel balance and safety, so this step demands total focus. Roundness and flatness tests are run on every rim. Specialized machines measure deviations to within fractions of a millimeter. The smallest flaw is enough for a rim to be rejected. Quality isn't negotiable. Then, mechanical fatigue tests simulate thousands of cycles under load. This relentless testing ensures that the wheels stand up to years of real-world riding. Crash tests are even harsher, pushing rims beyond expected impact to prove their resilience. The results are logged and reviewed as part of continuous improvement efforts, driving higher standards each production run. Throughout production, every variable is monitored: membrane pressure, temperature, layup sequence, and cure time. Any misstep can lead to weakness, so operators track data in real time and intervene immediately if anything is off. There's pride here. You see it in every technician's routine: the way they check alignment and layup symmetry, the careful handling of raw material. Carbon fiber is unforgiving. There are no shortcuts and no cover-ups. Final inspections are done in a separate, dust-free room, so nothing interferes with the surface quality of each rim. Environmental care is woven in as well. Optimized cutting layouts reduce waste, offcuts are recycled, and the factory environment is kept pristine to prevent contamination. The final wheels are feather-light, aerodynamic, and strong enough to race. Each one is proof of a process that values both science and hands-on experience. There's something mesmerizing about seeing fabric transformed into such a high-performance part. Behind each rim is a team committed to getting it right every time. A bicycle rim may seem simple, but its creation involves precise engineering. Steel strip enters the production line, clean, flat, and ready. It starts with flat steel strips fed into a precision press. Holes are punched at exact intervals. These will hold the spokes later. Watching this accuracy is oddly satisfying. The strip moves into roller forming machines. Each station bends the profile slightly, turning flat steel into a continuous rim curve. Then comes the cut. A sharp press slices each rim to the perfect length. No welding, just a clean break that fits tight. The repetition, the force, the timing, it's mesmerizing. Every press and punch gets us closer to a rim ready for the road. This is where a raw metal block becomes a precision-engineered component. The Hermel C60 UMT starts with heavy rough turning on a 1.5-ton billet, cutting away 935 kilograms using a 4 mm depth at 330 meters per minute. It shapes the outer profile while rotating the A-axis for full control. Deep hole drilling follows at 95 meters per minute, with a 0.34 mm/rev feed rate, essential for complex internal structures. Adaptive feed control continuously adjusts the cutting speed to maintain spindle efficiency. Then comes 5-axis finishing, where every curve is refined. Mechanical edge profiling removes burrs without human intervention. With a traverse range of 1,200 by 1,300 by 900 millimeters and 2,500 kilograms table capacity, this machine is built for large, high-precision parts like aerospace or energy components. Watching it cut with such force and accuracy is thrilling. This is machining at its most powerful, where skill meets automation.